Hello, and welcome to Locutors of Trek, the podcast where we talk about the people, places, and things of Star Trek. So, replicate yourself a Romulan ale or your Synthos selection of choice and join us far beyond the stars.
Hello, and welcome to Locutors of Trek, Season 2, Episode 3 on Astrophysics. We are your hosts, Davan and Dave, aka Plain Simple Tailors, and your Locutors of Trek. And of course, my captain and cousin, Dave Mader.
Hello. Thank you for having me, guys. I know this is a special privilege to be a third wheel here at Locutors of Trek.
Well, it's okay because we have a special guest with us tonight that actually knows what she's talking about, which is a rare thing around here. Dr. Erin MacDonald.
Hello. Yes, thank you for having me. I'm excited to be here and nerd out over this stuff.
Wonderful.
So,
as Davan mentioned today, our plan is to speak on astrophysics, which I know in some sense is a bit of it's a younger discipline from the early analysis of von Fraunhofer at the beginning of the 19th century, where he and another fellow who apparently, whose name I've forgotten, independently through the decomposition of starlight, learned to read the chemical traces in the sun's corona. This, what I think is appropriate, this is the birth of a new science from, it seems, the Zeus's brain of astronomy. So, welcome. We plan to explore the lovely firmament with you. So, if you wouldn't mind, just at the beginning, what is astrophysics to you?
Yeah. It's interesting because I think there's that innate curiosity about what's up there, what's in the stars above us, and that's kind of astronomy, right? Trying to describe what's above us, what the universe is made out of. And then astrophysics asks the questions why and how. How is the sun doing what it does? How did the galaxy form? How did the universe form? How is it continuing to expand? Why is it continuing to expand? And it's about applying our knowledge of physics to what we observe in astronomy. And the thing I really like about it is it's like this weird cyclical science, because most of what we study in astrophysics you can't just do in a lab. Even like the computer simulations aren't strong enough for some stuff. Like we don't even have the computing power to fully model what we see. And so we're in this constant cycle of like applying what physics we know to what we're observing, and then we observe more and we have to revisit the physics, and it just goes back and forth. And this was like the whole gravity debacle was, Newton came up with this concept of gravity as a force. And then in the 1800s, as we started to model better, we started to realize like Mercury's orbit wasn't quite right. And so that astronomy aspect forced us to revisit the physics of gravity. And that's what excites me the most about astrophysics.
Well, that's lovely. Actually, I was looking up to revisit things for our talk today. I was looking at one of those takes during that unstable period about Newton's gravity that has become one of my favorites, maybe for its audacity, if nothing else, which is this wonderful text, Cosmos Without Gravitation by Immanuel Velikovsky, where he tries to say that, no, it's just all the electromagnetic effect, like top to bottom. Which is wonderfully audacious, right? I don't think anybody necessarily agrees with it too much, but...
That's a great way of phrasing it. There are a lot of people still out there who, I say a lot, there's numbers of people who don't believe that Einstein's general relativity is the right way to describe gravity. I don't personally subscribe to that, but again, because we're in that weird space of astrophysics that like you just have to apply models. So if someone's able to come up with a model that explains it, then they can go down that path pretty quickly. But it's pretty hard to do.
Right. Yeah. Yeah.
Interesting.
So thank you for that.
So I have a question about our galaxy. Is in relation to Star Trek. Does Star Trek make the Milky Way seem too small, do you think?
Yes. Definitively. But it does a decent job. I think most science fiction, it's really hard to appropriately convey distances in a science fiction where you are leaving our star system. The nearest star to us is over 4 light years away, meaning it takes light, the speed of light, 4 years to get there, which for a 5-year mission is dire. So, you want some interesting things to happen, which is, of course, where warp drive came in to sort of shorten those distances. But certainly, I think that's one of the hardest things to convey is, we call it the cosmological address, that you have like your planet, which is in a star system, which is in a galaxy, and the scale difference between those is vast. And so sometimes a lot of what it is looking at what Star Trek maps we have, that I think the shows try to do a good job of staying true to, some consistency about like where Vulcan is or where Rice is or the Klingon Romulan border and all of those things. But you still need stuff to happen. You can't just be in warp for ages to try to reach the next anomaly. So yeah, I think the show that probably did it best was Voyager. Obviously, the whole conceit of the show was trying to traverse this vast distance across this whole galaxy. But even then, it's hard to wrap our minds around how far that actually is, for sure. And to note as well, the whole concept of the quadrants is a purely Star Trek thing. That's not astronomers haven't delineated our galaxy into those quadrants simply because there's so much dust and gas that when we look down the plane of our galaxy, we actually don't know. We know what's out there, much, much further out there. It's even hard for us to map out our own galaxy because there's so much stuff in the way. So, which, Star Trek does address to some extent, with the Delta Quadrant being and the Gamma Quadrant being mysteries to some extent. But yeah, it's the galaxy is very, very, very big. Space is big.
Yeah. I was going to ask you about the quadrants actually, because it always seems strange how like the alpha and beta quadrants are kind of so familiarized with each other, yet like the alpha quadrant's just as close to the gamma quadrant as it is to the beta quadrant, but it's this great big mystery and things like that. I always thought that was kind of
Well, and how much they interact with other galaxies is pretty limited in the show, because of course our galaxy is massive, but it's one of billions of galaxies, trillions of galaxies. I don't think we even know, right? How many there are, but there's only like a couple episodes of Star Trek where like they're dealing with the Andromeda galaxy in that episode in the original series with the Kelvins. Where they're coming to conquer our galaxy because it takes 300 years just to, even at warp speed, to travel between these two galaxies, and that's the closest galaxy to us. So lots.
Yeah, and then they wanted to kind of address that as well in season 4 of Discovery, about just civilization just outside of our own galaxy, like not even in another galaxy, but just kind of beyond what we would consider the Milky Way. And so yeah, you're right. Like Star Trek, I do think does a good job, even though the distances might seem a little bit warped. Like it does do a good job of constraining it to our galaxy. It's not getting too far out there with distances and stuff.
Right.
You mentioned scale. Speculate if you haven't crunched these numbers for some reason. Why you would? It's about Star Trek, but because we were talking about warp and how long it would take to get just different stars and stuff. How long would it take at warp 9.9, let's say, do you think, to get to another galaxy? Because we're talking about scale, right?
That's a great question. To get to like the Andromeda galaxy is sort of our biggest sister galaxy. I'll crunch the numbers. Can we quickly? I'm gonna look up.
Yeah.
I don't know. I don't memorize numbers.
At least a couple
Sure.
centuries, probably, right?
Well,
Like so.
I would think,
Yeah.
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 So, speaking of other galaxies, brings me, maybe while you're taking a moment to pull up those numbers, makes me think
Just crunching the
about
numbers.
one of those analogies that sits in my head that I don't actually know if it's real. I'm a big microcosm, macrocosm kind of guy. And so one of the things that I often think about is that, the structure of our own solar system was so impressively demonstrated when Voyager went through the heliopause a few years ago, right? Many, 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 many years, as space is big, after it was launched. And I always think about that as sort of like the almost, the cell wall of the solar system, right? If it's this sort of plasma, helium, whatever it is, sort of sheath or skin that the solar system has. Star Trek speaks of a boundary around our galaxy, an energetic boundary. And that seems to be something that they've even hinted at, maybe is constructed or is for some good reason. But is there some sort of a way that we define the boundary of a galaxy in that way? Like, does a galaxy have a galactopause as opposed to a heliopause in the solar system?
I'm so glad you asked this. So this was a weird rabbit hole that we went down, because when they wanted to do that, they wanted to have Discovery encounter the galactic barrier in
Okay.
a callback to the original series, right? Like that
Right.
was a story, but it was all very philosophical. Like it was much more of like the psychological impacts and like the weird energy barriers and stuff. And so, they asked like, is there any science to a galactic barrier? And I went down the exact same path that you went down, where it was like, well, we have a heliopause. Like we have this like spike of radiation that's all these massive, low mass, but massive radiation particles that didn't have enough energy to escape the gravity of our sun. Like,
Mhm.
could there be the equivalent in the galaxy? And so we came up with like a galactopause, was like exactly that thought, that there is like this radiation barrier. And weirdly, like that same month, like I had started to see paper, like there was a paper published by one of my old professors, ironically, on like thinking about the galactopause around other galaxies. Like, can we detect this? Is this a thing?
Wow.
So yeah, like it is definitely something that people think about now. Like the psychological effects, the physiological effects,
Mhm.
that's more the science fiction. That's more harkening back to the original series for sure. But
Sure.
yes, that's definitely like possible, which is awesome.
That is super. So how do we actually define the edge of a galaxy now?
Now it has to do with just where the density drops off. Like
Okay.
you have a pretty clear cliff where the density of the stars, and it just has to do with the angular momentum and the rotation patterns. Like there's a cliff to the density of how many stars per area, and that's roughly the edge. There's a pretty big plus or minus light years
Sure.
attached to
Sure.
that, but there is
Yeah.
an edge to it.
But so too with dense forest and a farmer's field. Yeah.
Yeah, exactly. Yeah.
So you mentioned psychological effects. So here's something I wonder about, because we talk about wormholes, and Star Trek uses them to travel. So the Gamma Quadrant wormhole we have, and of course the one in TNG where the Ferengi go through. But they always seem, and even in other things like Farscape and other science fiction, wormholes, it always seems so calm in there. I just feel like you couldn't fly into a wormhole and it's just kind of like a nice calm day and it's all trippy all around you, and then you get to the other end. Like, wouldn't there be gravitational forces, and who knows, like you wouldn't just pass nicely through a wormhole theoretically. I know they're theoretical.
No, good question. Yeah, so wormholes, are this mathematical construct that like the math checks out. We've just never detected one. But it is this idea that you can connect 2 points in space-time, especially if you think of the idea that our local space-time might not be flat. Like we're not, we have that trampoline analogy where space-time is sort of this big flat trampoline, and then massive objects create these gravitational wells on them. But it could have local bumps, ridges, folds, whatever, and that traveling on the surface takes a long time, but you could punch a hole through it and actually have a shorter distance. Now, the big problem that we don't really address in science fiction is like what happens to you while you cross the event horizon of the wormhole, because that's essentially the same topography as a black hole, which spaghettifies you. Yeah.
So warp
Chills
drive
up.
would be as bad as the transporter under Mohammed Noor's understanding, which we talked about a while ago. Just a murder machine. Right.
Exactly. Yeah. So, but once I guess it really depends too, kind of how long that wormhole has been there, if it's naturally occurring or artificially occurring. The Bajoran wormhole, the Deep Space Nine wormhole, like that is a naturally occurring wormhole that sort of its aperture opens and closes over time. And I do like to think that there is actually stuff in that wormhole, because we have the wormhole aliens, right? And the way I love to think about it is, if we go back, this gets a little bit heady, but I'm super nerdy about it. If you go to
Please.
if you go to our space time being this, like that we think of time progressing 1 second per second, and we have our laws of physics, but the Barzan wormhole, or not the Barzan, that's the other one, the Bajoran wormhole interacts like this. That's why their knowledge of time is like completely perpendicular to ours. Like they experience all of our time at one time, and they have their own linear progression of time that we can't understand. And so like it has to do with the alignment of the space times between the wormhole and our own. It's almost like it's a different universe in the way it's constructed, even though it's part of our own universe. Its topography like isolates it.
Pocket universe.
And so yeah.
Right. Well, and we see examples of some of those. I'm thinking about, and somebody's gonna have to help me with the name of the episode, but I think it's a season 1 or season 2 episode of TNG where they find themselves in a weird hotel and they're looking for, they end up finding an old dead astronaut in there.
It's like the Royale or something.
The Royale, that's it. That's right. And it seems to be playing out this wonderful noir story, but what is in reality happening is this strange little pocket universe almost. That seems to be something, that the prophets are able to sort of control at their leisure.
Right. That this idea is like when you're warping space-time like you do with a wormhole, that you can create pockets where time exists differently, which is valid. I mean, we even have that in the animated series where they have like the Bermuda Triangle pocket universe thing, right? Where time exists outside of our own time and ships get stuck in there. And there's lots of great examples in Star Trek of that, for sure. And of course, Frasier getting stuck in that.
Of course.
Yeah.
Captain, what was his name?
Frasier. Captain Frasier.
Yeah, Captain Frasier.
Everyone knows what I'm talking about.
Yeah, exactly. Apparently, the Vulcan next one was supposed to be Savick, supposed to be Kirstie Alley. So
really?
Yeah. That's why they got him. They thought it'd be funny, and then Kirstie Alley wasn't available, so they just put this extra next to him. And they're like, "Why is Kelsey Grammer here for 2 seconds?"
Speaking of time, let's talk about warp drive for a minute, shall we? The time dilation effects of warp drive they say is like canceled out by the warp bubble. Wouldn't those be kind of handy, actually? Like, wouldn't it be handy that you just get to a place 5 minutes after you were talking to somebody because you like allow the time dilation, or does time dilation work the other way around?
It works the other way around.
Yeah,
so
okay,
they'd be waiting for you for ages, and you'd get there pretty soon.
Okay,
but the hard thing with so that's special relativity, and the key with special relativity is that effect exists below the speed of light. So basically, when you're pushing impulse drive to its limits, Now we don't. It gives me a headache to think about this stuff, and I had to spend a semester like learning this. Like it special relativity, that's the twin paradox. That's all of these, you go
Mhm.
99.9 the speed of light, you're going to age differently than people on Earth. But you're right, just to address it quickly, before we get into other questions, the idea with a warp bubble is that, first of all, that's going faster than light, but you are insulated from that because your ship is not pushing those limits inside the warp bubble. You're not creating that relativistic environment. It's that space-time is wrapped around your ship, but the laws of physics are staying the same. And so this bubble is carrying you, but you're not compressing or extending space-time in a way that would create that sort of twin paradox effect conveniently.
Right.
My follow-up question then would be about impulse drive. If that's the sublight speeds, then shouldn't the time dilation maybe come into effect in some of these Star Trek stories? I don't know how they account for it.
One of the things, as I understand, if I can just jump in for a second, is that maximum impulse ends up actually being about 0.25 C.
Yeah, it's
So-
not. Yeah,
But it does make me ask this question to follow up on what Dave is saying. If that's actually what like top speed at impulse drive is, if you were to say find a wonderful Scottish engineer in down by the plasma manifolds for the fusion cores for the impulse drives,
I'm a drink.
and you were able to push well past that limit, could you do something like the Picard maneuver sublight?
that's
Just appear.
a fantastic question. I mean, I guess
up with the
so. I
zingers.
think I like to think that the limits of the impulse engine are for both logistics as well as time dilation nonsense. So,
Personal
like,
safety.
yeah. So when you talk about like if you're able to push the impulse engine to basically thread the needle that shouldn't exist, which is sort of a weird way of thinking about the Picard maneuver. Like,
Mhm.
yeah,
Right.
I wouldn't do it, and I certainly wouldn't trust cadets to do it because it's always so. A good analogy to this is the horse and the barn paradox that we talk about with special
Okay.
relativity. That's like if you have a barn that is exactly the size of a horse, and a horse is running at the barn at 99.9% the speed of light, like the horse starts freaking out because the barn looks smaller than it is. You are like, oh, this is a piece of cake because as the horse is approaching you, it looks smaller than the barn is. And so this is the weird relativity aspect of special relativity is like which one is right. And it depends on the observer. It depends on what we are considering the reality, which is why cadets should not mess around with the Picard maneuver. But-
Fair enough. Nova
but I do
Squadron,
like-
we're talking to you.
Red Squad.
A Red Squad,
Right.
that's what it was. Yeah.
There you go. Yeah. And, in the 0.25%, like that's the thing too, is the impulse engine they really use for short trips in a solar system, which even
Mhm.
then are not insignificant distances. Like they're still covering a good distance, but it takes time to do that. A good comparison to that is the Expanse, because I think the Expanse does a good job because they have a constantly accelerating engine that's accelerating them at 9.8 meters per second squared, which is gravity. And if you crunch the numbers, basically by the time you get to the outer edge of our solar system, that heliopause, you're going the speed of light. Like that is the limit you can go. And so,
Salamanders.
yeah, exactly. Yeah.
Well, I was just with the whole speed of light thing. Sorry, I lost my train of thought. I completely lost my question.
Sorry, I
Well-
took us on a journey. That was my fault.
Indeed.
If you were to put on your futurist cap for a minute and peer into perhaps the 24th or 25th century, and humans are traveling between the stars, do you think it would be by warp drive, transporter, or just not going to happen.
Even sleeper ships or something like that,
Ooh,
or
sleeper ships. I think that mathematically warp drive can happen. We just have to make an unforeseen leap in energy technology that we just can't predict how long that's going to take. So whether that takes, what are we now, 40 years out, or whether that's 140 years out, that will dictate when warp drive is available to us. I worked in gravitational waves. I do think that that's possible. Like, the more we're learning about how space-time moves, the more we can learn how to play with it. But it just is going to require a ton of energy to do that.
But this is more than fusion reactors are going to be able to generate for us, right? And that's part of the trouble, to my mind.
Yeah.
Because fusion is something we just can't make energy profitable yet, but you can make it happen. But this is an order of magnitude, it seems to me, greater than that, which is why warp drives in Star Trek rely on dilithium crystals and antimatter matter annihilation.
Right, exactly. They're relying on matter-antimatter reactions that are harnessed. That is, again, a technology we don't necessarily have right now. And when you talk about the fusion, that's the energy kind of stored in atoms. Now, fission is like a nuclear bomb, and that equivalent, I think we need like that was a teaspoon of matter, and to get a warp drive to work, that was like a semi truck size of matter. Like, so that the energy scale is like not something I would go near. But my joke is like, I get why Zephram Cochrane drinks. I was strapping myself to that. I would be pretending it didn't exist too. So yeah, like that's the limiter right now. So I do think whenever we reach that limit that we can travel between stars, that's going to be how we do it. I hope it's sooner rather than later, but who knows?
I remember my question now. Okay,
Yes.
so this is more shown in Deep Space Nine than anything else, where this idea of like you can't go to warp inside of a solar system because I guess you would run into things or something. Like, I guess is the idea, like there's asteroid belts, there's more matter.
It's because you're bending space, isn't it? It's because you're bending the space that's too close to planets. Like,
is that what it is?
Yeah, it's like the question I wanted to ask too about the TNG episode where like they're talking about environmental degradation basically in space because of high warp. Same thing, it's because of the bending of the space, right? And like it just doesn't always bounce back perfectly after you've done it a whole bunch of times. Is that sort of what's happening there, right?
So the way I think about it is a combination of what both of you are talking about. Like, it's that you're too close to planets, moons, asteroids, whatever, and that there's too much debris. And if you combine both of those explanations, then the major risk that you're taking in is not so much damage to the ship, and it's not so much damage to the planets themselves or any other body that, the M-class world that people would live on. It's that you're disrupting the gravitational equilibrium of that star system. So you're essentially like, as you build your warp drives, stuff can start getting flung around in directions that it is not predictable or stable. Because that's the thing is, our star system now has equaled out in the sense that like we have Jupiter kind of protecting us from a lot of the, we have the asteroid belt that lives between those and the Kuiper belt. All of those have like settled out over the billions of years that our sun has existed. And a huge gravitational anomaly such as warp drive forming could disrupt that. Is it lethal? Maybe not. Is something on the scale of like Zephram Cochrane's warp engine? Definitely not, because that was like 0 scale, right? So that's not going to be as much damage. But going to like high warp in a star system just runs a risk of threatening the stability of the star system. That's how I view it.
Yeah. In that episode, there's an episode where they're like the Dominion's trying to destroy Bajor and the solar system by triggering a supernova, right? And so the Defiant is like near the wormhole, which is on the outside of the solar system, I guess, like equivalent to where Pluto is for us, I think, in Earth, right? So they're like, well, we're too far away, and Kira's like, take us to warp, and she's like, inside a solar system. She's like, if we don't, there won't be one left, and they do it, and they go and they get the changeling, and they flung him into the sun, and that's the day.
Great.
But I guess like the Defiant, not a big ship, but obviously it can go very fast. So how much of a risk did they put the Bajoran star system at in the process?
Yeah. I mean, it's hard to tell. And one thing I always say too is the way I think about the different factors of warp drive are dependent on the size of the ship. So like the energy required for a Constitution or a Galaxy class to go from warp 1 to warp 2 is vastly different than it takes the Intrepid class, our little science vessel, right, to go from warp 1 to warp 2. And so for me, I view all the different warp drives or all the different warp speeds as relative. And so like you said, the Defiant is much smaller. So it's going to have a smaller impact, and it just depends on how risk averse people are to performing that.
So if I'm understanding correctly, we go back to that classic, rubber mat analogy with various sizes of, marbles on it. This would be, if a fleet were to go through a system at high warp, this would be like rolling marbles of various size just through your model, willy-nilly, and just seeing what's going to happen.
Right. But with a big asterisk of like the size scale differences are huge, so we talk about the distance between our star to Alpha Centauri, and that's 4 light years, and that's the equivalent of like a baseball in LA and a baseball in Denver, Colorado. Like that, there's huge space difference between those. And there's also a great website I can recommend to just kind of try to wrap your mind even around a solar system. It's called If the Moon Were a Pixel. And basically you just start at the sun and you just hit your right arrow and just sit and just watch. And like, good luck getting to Saturn before you give up for whatever reason.
It's a big way to spend an afternoon.
It's like that poem Data has with like long periods of silence in it.
Exactly. So that's where I feel like even though we talk about those risks, you do have to remember like stuff is still really far apart, even within a star system. And so you're not really running a risk. Like your fleet would have to be absurd to have an effect on a star system like that. Yeah.
As long as your deflector shield's working. It's like in a comic we just recently reviewed. It's like Tom and B'Elanna, and they have no deflector shield, and B'Elanna's like, just get us up there and then we'll worry about it. He's just like, B'Elanna, I do not want to go up there without a deflector shield at all. She's just like, we'll worry about it later. He's like, no. Like,
It's a big step.
Yeah, it's a big step. But yeah, the deflectors. I don't think it gets enough credit in Star Trek how important the deflector dish is.
It's true. I agree.
I have one more follow-up question
go ahead.
on this whole topic, because I'm like, okay, let's say you could invent warp drive. You have the energy to do it, but it sounds like there's kind of like a danger to it. You could like create these gravitational effects. You could disrupt your solar system. So let's say you invented it, like it seems like not a technology you would want to let everyone have. You would want to control that. I guess we're getting into more philosophical.
It's the Romulan perspective.
Right. But like, I don't know, like we know that people will speed down the highway just for fun. How do we know they won't speed out of the solar system and knock Jupiter off its axis? And then all of a sudden, we got an asteroid coming at Earth or something like that. It's
drag racing through the solar system.
Right. Yeah. I guess I'm just like, maybe even if there was space travel, like, could you be like just an independent person who bought a ship and you're going around and
I mean, I would equate that so maybe not so much with like cars, but maybe with airplanes, right? Like airplanes in the wrong hands could still cause a lot of damage. So it would require a lot of regulation in the way that we regulate airline travel more than how we regulate cars. That there is a matter of like people are observing what's going on. There's communication across nations and companies and all of that to just say like, who has this capability? Who is licensed to do it? Have these standards of, so that's more what I would compare it to than drag racing.
Mhm.
Right, okay,
Just because
okay.
it's
There's an
effectively
aspect
easier
there
to get a license with that. Yeah.
Yeah, and I think there's an aspect here in terms of Federation society that comes in where, I mean, if you think about how, say, Annika Hansen's parents get their ship, right? They apply for a long-term loan, I think either from Starfleet or whoever makes ships for Starfleet, that particular one, in order to go out and do some kind of study, right? But the Federation says, that sounds like a good idea, go for it. We'll make sure that happens in that sort of post-scarcity, post-currency, human-oriented way that Starfleet likes to do things. But if you think about other forms of space travel, which are not being guaranteed by either the government of Earth or the Federation, it falls back to one of my earliest encounters with sci-fi, other than Star Trek, which is, because I am a massive nerd, the role-playing game Traveller. Which is it's quite hard sci-fi, but it's wonderful, and it's often been called either Spreadsheets in Space or Truckers in Space, because to get yourself into space on a free trader is going to cost you 42 million credits, and so your character begins the game with a mortgage. This is, you can imagine Captain What's His Face and La Sirena. He's not operating in a non-currency environment. That guy may owe 37 million jibblewops to somebody out there who's going to come calling if La Sirena is not producing by cargo. Right? I think there, in some ways, there'd be a massive investment, like a shipping and freight company not wanting to, lose its ship around the, Cape of Good Hope. As important as that is, would be as important as making sure the trade routes past the Zenkethi are clear this year.
Yeah. No, that's a good comparison. I like that.
Yeah.
Before we move on from warp, and we mentioned,
sorry, I brought it to mortgages. I apologize.
Love it. No, it's
if there's any hard science behind the forced singularity drive that the Romulans, like, is it something like CERN or something is trying to work on or something like that?
So the Romulan faster than light drive I really like, and I have it's not perfect. I'm going to preface this, like, don't scratch too far beneath the surface, but how I think about it is like exactly the carrot on a stick type of approach, where it's like they basically dangle a black hole in front of their engine, so their whole ship is constantly falling into a black hole, and like that's what's causing the acceleration that allows them to warp space-time. Essentially, like, their warp is more a localized black hole than anything. It's a singularity that they're talking about, and that's consistent with how they talk about it. But then you start to ask too many questions about, like, well, it's not really faster than the speed of light, but relativistically it could be considered, because people are perceiving how fast they're moving different, and so there's an element of like secrecy to that. That was kind of what we saw with the Pike maneuver, right, where he kind of slingshot around the black hole. That's kind of like Romulan nonsense that they're dealing with, this dangling that.
Romulan ships are slower too.
Right, they are. Yeah, exactly. And so I always thought about it that they literally have a black hole that they're able to, because again, we think about space-time and it's hard for us to convey it. We use the trampoline, but even that's shrinking it to like a 2 to 3D space. We have to start thinking of like a 4D space, which is really hard for our brains to get around. And so you think about that, you can technically dangle a black hole in front of an engine in a 4-dimensional space and allow that ship to fall into it and accelerate forward in 3D space. It's really hard to wrap your brain around.
But it would be like falling downhill with a sort of gravity wave running in front of you almost. That's right. That's the sort of front of your, like a toboggan or something, right?
Yeah.
I mean, it sounds like an insane thing to do, let's be honest. But it also sounds like a pretty Romulan maneuver.
Right. Well, in the video games, in the video games, like, they're slower when you destroy one of, like, in like Star Trek Online, which, by the way, we have to talk about, because I'm a huge fan, and But in Star Trek Online, when you destroy like a Romulan ship, you like watch like this black hole like suck them up and crush them. And they have this immense power in their ships because they have this black hole. So their weapon systems are so much more powerful, and they can destroy Starfleet and whatever else they like to do. So it's incredible. Okay, but I feel like this is the point where I have to talk Star Trek Online because I just played a mission. Well, I played it several times now because in the game, as I have a few different characters. Davan knows much about this, but Erin was just a character recently in Star Trek Online, playing basically a version of herself. A member of Captain Harry Kim's crew on the USS Inouye, where they're fighting not just the Borg, but the Mirror Borg.
You can rest comfortably knowing your captain earned his position.
Like in the game, just to show you here, like here's Erin.
Hey.
There you go.
In the game,
Erin MacDonald, Astrophysics.
He respected your
We need
credentials.
all the help we can get against the Borg.
I played this several times now. It is
He
incredible.
appreciated your help on the mission.
Yeah. Going through the mission and everything else, it is awesome. You did such an amazing job playing yourself, but like a character in the game, like who's like helping along with things. You have some great scenes with Garrett Wang in there as well, which I really,
We can't let them take the protomatter tech.
I'm on it, Captain.
Huh? You're an astrophysicist, not an engineer.
Actually, sir, I minored in engineering at the academy.
What are you gonna do? Make it fast.
Make it fast, Commander. So, which always kind of spurred my imagination too, where I was like, well, that's kind of true. Like in Star Trek, we always say the engineers are over here and the scientists are over here, and they're separate. But your character says I'm both, and I looked up your credentials. You are both in real life, and so I was just like, okay, well. What I guess my question is, why do you think that is that we in Star Trek say that like Scotty is this thing and Spock is this thing, but you can't be both because obviously both have scientific principle involved.
Yeah, that's a great lead into that question. First of all, it was awesome being part of it. Instead of this being the Kurtzman era, we're trying to create the Dr. Erin era, multiverse.
Right, because you're also in Star Trek Prodigy, playing a version. I'm like, is this the same person? Like, because
Yes.
That Erin MacDonald is in the 2380s, and this Erin MacDonald's in like 2411. So there's like 30 years apart. So it seems like
time agent.
Time
right.
Agent.
So yes. And in the first appearance that I ever made was in the season finale of season 2 in Lower Decks. If you listen carefully, Shax shouts, "Dr. Erin said we can't do that."
Oh, okay. No, I didn't.
Oh, nice.
Of a bunch of other dialogue. So somehow I know Shax. Oh, and in the comic series by Mike Chen, The Dog of War, which if you haven't read, okay, great.
Yeah.
Jadzia Dax sends a message. She says, "I reached out to a friend of mine at the Daystrom Institute," and the pad comes back from Dr. Erin MacDonald. So,
Man,
I'm friends with Jadzia. I'm friends with Dax. I work for Harry.
This is canon.
So what you're saying is we're going to have to interview you in character as Erin MacDonald as well at some point.
Right. So there's lots of theories. One is that that's my ancestor, which is boring because I want to be there. I don't want to wait for some ancestor. Or at some point in my personal future, I will voyage home my way into the Star Trek universe through time travel. Or I'm a Q. Those are the prevailing theories.
Oh,
okay.
yeah.
I like all of them, but to genuinely answer your question about science and engineering,
Yes.
I think it's valid, and so my personal career trajectory, pure science. Like I went through like the College of Arts and Sciences. I had fellow engineering majors alongside me, but we took fundamentally different classes. Like my degree was different from theirs in how I was taught. And then as I went through graduate school, I ended up basically becoming a theoretical astrophysicist. So everything was just coding, modeling, calculations, not practical whatsoever, zero practical. And then career trajectory changed. I need money. I couldn't have my visa anymore, and I'm trying to figure out what I want to do. And so that's how I got into aerospace engineering. And what was interesting about that was how many similarities there were once you started doing the work. So it was basically like I was working on satellites. And so instead of telescopes looking up and doing data analysis, we have satellites that are looking down and we're doing data analysis. But it's that practical aspect of how they chain together and how the system functions, systems engineering. So once you do it, you start to see a lot of parallels, and a lot of training applies across the board. But it takes that level of effort to learn
Mhm.
both disciplines and to start to understand how they both work. I could have worked my entire career in theoretical astrophysics, and I could not have told you how a satellite system works ever, like for the life of me. And so, that's and there's people who work in satellites who could not derive general relativity equations, like because they never have to, and so it is just specializations.
Mhm.
But there is a lot of shared background info. So the leap from one to the other isn't insane, but it does require some level of effort. And so
Right.
Spock has no interest in learning how the intermixed chambers of the warp engine are required to function, but he knows theoretically how they do.
Right. Yeah.
It's up to
And there are
Scotty to
episodes where they team up, or like,
right.
we need both of them or whatever. But
Mhm.
then you have characters like Data and even Harry Kim, I think, as well, who are kind of both. Like, like they wear the gold operations uniform, but they're as much the science officers of their
Mhm.
respective ships as anything else as well.
Well,
Well, and we
this.
see too sorry, just real quick. We see too in
No.
engineering that like there's a lot of people who know very little about a lot of stuff. And that's kind of where I fall. That's where my career has kind of ended up. And then there's people in their careers who know everything about this one thing. And so
Mhm.
that's kind of how you start to team up and work together, that the people who kind of span this can then call in the experts on those very
Leah
specific.
Brahms, she comes in
Right.
as the warp expert.
Yeah,
Right.
exactly.
So one of this sparks a question for me, because part of what you're talking about there is sort of disciplinary formation, right? So what the sort of like materials of your discipline are as compared to an engineer's sort of focus. But it seems to me that Starfleet also has a sense of a culture between those two branches. Like I'm a classics guy by training, and there's this ancient difference that, say, Aristotle will make between a chirotechnos, who is a hand worker, and someone else, the philosophus or someone else like that, who is more of a mental worker, right? And it sounds, and your experience has bridged both of those things. One of those lovely, what is it, Metropolis, hands and head meet through heart or something moments, right? One hopes. But so my question is, do you think that some of that sort of hierarchical reality is still in the sciences now, or do you think that was more a picture of, say, the sciences in the 60s when we first see Star Trek, and that those echoes carried, but do you think they're really still there?
I would say that they're really still there, and I think it goes down to just the our philosophies of education have carried on, centuries past, where the difference we're looking at from TOS to now, right? And
Mm-hmm.
the disciplines of, because a lot of that was rooted in like military assignments and naval assignments and
Sure, yeah.
specialties. And I would say that hasn't changed now, but I don't think it will change. I think that, like you said, there's people who have a proclivity more towards the theoretical side, and people who, have a proclivity for the engineering hands-on
Mm-hmm.
aspect. And that's what I like too about Star Trek Prodigy, which if you haven't watched, it's on Netflix now, so people can go and watch it. And
thank
please
you.
binge it. Just throw it on in the background.
We've watched it. We've watched it.
Yeah. But one of the fun things
It's
with that
great.
was that we had the character Rock Talk, and her big motivation is that she likes science but doesn't know what kind of scientist she wants to be, and sort of spends that season figuring out and trying different disciplines and realizing that like she's not cut out for some stuff. And like that was a big part of my own personal journey of like I just like science. But there's some stuff I'm good at and some stuff I'm not good at, and we have to figure that out. And the way we divide, our understanding of the natural world, there are people who are more I suck at biology. Like I'm terrible at biology. I don't have a brain for biology, but I have a brain for math and physics. And so
Right.
I don't think that's a bad thing, and I do think that'll carry on to our Starfleet future for sure.
Right.
Yeah.
Yeah, I mean, we're
Just
complementary
speaking
to
of biology,
each other, right? We need each other. Yeah.
One question I like to ask everybody, because it's been interesting even so far. We've had two guests this season; they had completely different answers. Your friend Mohammed Noor had one answer, and then on the next episode we had a metaphysicist on. He had a completely different take on this question, which is the transporter a death cloning machine or the safest way to travel?
I okay, the joke, but like the me answer personally, like I agree with Hoshi, like do not put me anywhere near that transporter. Like it is a death machine. Like I want nothing to do with that. And yeah, a death clone machine. Like that's how I see it. um and because I think of it, when you think about the science of the transporter, right now it can't exist because we're not able to, because of uh, Heisenberg's uncertainty principle.
Yeah.
Yeah, that like we can never pinpoint exactly where all of our particles are. And you need to know that. And if
Right. Yeah,
so,
we
if
don't
you're
wander
thinking
around
about
with pre-entangled buckets of particles for ourselves.
right,
Yeah.
exactly.
Well, this guest said we were going to throw it all away anyway, so we didn't need to know. That was his answer.
That's right. 90% of you were just gonna chuck
Yeah.
like a JPEG.
Yeah.
I like the
Yeah.
pre-entangled bucket of particles. That's how I start to view the human body, right? Which is just like a sack of meat held up by bones. That has
Mostly
feelings.
water.
Ugly bags of mostly
Mostly
water.
water.
Yeah.
That's right.
We're all just cucumbers with anxiety, right?
Oh man, yeah. Well, I mean,
Um,
Stuart Hameroff and Roger Penrose, that's their model of consciousness, right? Is in a network of non-local entanglements.
Yeah,
Some
and
of us
more
in
pickled
that
than others.
sense, we have no knowledge of how to replicate it. Yeah, like we don't know enough about the entanglement, not just entanglement in general, let alone in our own brains. So yeah, I'm not getting near a transporter. No, I'm good.
So another question I have is, earlier in Trek before Voyager, we would hear of stellar cartography in like that department. We wouldn't see it very often, but we'd hear about it.
The
But then
Delaney
Voyager,
sisters.
of course, they update. Yes, the Delaney sisters work over in stellar cartography for sure. But then, of course, Voyager upgrades it to astrometrics. So I was wondering, what would be the big differences there? What would the astrometrics lab do that the stellar cartography lab doesn't do?
Yeah, I view that as the difference between astronomy and astrophysics. I think that stellar cartography is mapping out where stuff is, and astrometrics is taking the yes and approach to like, where is stuff going to be? What is going to happen? Can we predict what things are going to look like? Like there's an element of complexity and modeling to astrometrics that we don't necessarily get in stellar cartography. But that said, even now, a lot of casual usage of astronomy versus astrophysics sees them as fairly intertwined. Like they're sometimes exchangeable the way people are talking about them. And so to that extent, I think I'm not going to like get upset if someone's like, that should really be stellar cartography. Like I think they're fairly interchangeable on a casual level, but I personally think there's a complexity to astrometrics that stellar cartography doesn't have. And they needed to have that in Voyager, right? Because not only were they trying to find their way home, but they are also mapping and making all these new discoveries. So they're putting a lot more information into the astrometrics lab than just simply mapping out what they're passing. Because Janeway
Sure.
goes, shiny.
Yes.
There
I love
really
shiny
is
things.
coffee in that nebula.
That kind of spurs a question for me, because coming into this day, so just for me to flex for a second on my astrophysics cred, I once got the chance to visit the NASA facility in Maryland where they built
Nice.
the James Webb Telescope many years ago, about 9 years ago. At the time they were building it, and I got to kind of go through all the different labs and see it. But my question has to do with what it's discovered more recently. It went up into space. I remember they showed me at when I went there, they showed, like, here's the moon, here's Earth, here's the moon, and here's where this thing is, right? It's still technically an orbit around Earth, but it's so far away from Earth you wouldn't even necessarily think about it. And it's replaced the Hubble telescope in terms of being our strongest way to look at the observable universe. And my understanding of it is that it's upset the whole apple cart among the astrophysicists, because recently some images came in that show galaxies forming what we thought would only be a couple 100,000 years after the Big Bang. And there's even some thoughts that, because we'd said, okay, well, the universe is 13.8 billion years old. I've heard it my whole life. That's what it is. But they're like, maybe not. Maybe it's much older than that, or maybe there isn't really a beginning to the universe. Maybe like the universe is kind of more, it's different than what we can think about that. So I guess my question is, what's your reaction to all of these discoveries and new information? And I guess how it might be challenging sort of these strong theories like the Big Bang, which have been sort of entrenched in scientific lore or in thought for some time.
Yeah.
And stars, because they go there.
Right.
Go to the Big Bang.
You described that really, really well. I think that this discovery of, because it's essentially, we have the order of events from what we consider the Big Bang, the birth of our own universe, where, what we call recombination, but it's really combination. It's all the protons and neutrons combining to become hydrogen. And then this evolution happens where those start to clump together and they get so hot that they become stars and they fuse and they're making helium now. And then they run through their life and spit out more elements. And then those stars come together. And the way we've always thought of galaxy evolution based on Hubble, and Hubble especially was the person who kind of really defined this, was that you have these like nebulous galaxies that don't really have much shape, and then they collide with another nebulous shaped galaxy, and collide being the operative word because stuff is so far apart it really just gravitationally interacts with itself, and then it forms a spiral galaxy that has many times more stars than what they started with. And that was always kind of the understanding of galactic evolution. And then, like you said, the JWST has now seen these galaxies that seem much further along than that 100,000 years should have allowed. And so where did they come from? How did that happen? Lots of cool stuff, no answers. But this is what I mean. I mean, this was what we started about, was this idea of astronomy and astrophysics, and our understanding now is contradicted by what we observe. And galaxy collisions to create a spiral galaxy, I mean, that's something that was like an assignment as an undergrad in astrophysics. Like, we had to build an n-body model simulator that showed two clusters colliding and that they eventually, angular momentum takes over and you form a flat spiral disk. And so we don't know. There's lots of great theories about where our universe came from. I personally love, we can never prove it with what we know now, but the dripping black hole universes, that this idea that you have a sort of parent universe that has a black hole that gets to a certain mass and it essentially explodes, but it gives birth to another universe. And then that's the dark energy that's pushing our universe apart, is that mass continuing to fall into the parent black hole that we can't see. Now,
because that would be the entire frame of, like, that would be like behind the cosmic microwave background radiation, right?
Exactly. Yeah. This is it's black holes all the way down, right? Like that's the idea.
Curiously turtle shaped.
Exactly. And so we don't have any way to prove that, but this idea, but I like it philosophically. Like for me, it clicks. Now, observing galaxies, that to me just implies the shape of our universe might be different than what we're thinking of. Maybe we're seeing some warping lensing effect, it's like we're looking back in time, but we're seeing like a mirror of the other side of our universe time wise, right? Because everything's expanding away from each other. So the stuff that went in that direction during the Big Bang, now we've gone in this direction. We're never going to see them unless the universe has a certain curvature to it. And so,
like a kaleidoscope.
exactly.
One of our earliest analogies on this show. Yeah. So where does
This
the
does bring
koala
me to a
fit into
question,
all of
though.
this? That's what
Yeah,
I'm
well, because just to finish the thought, like
Sorry, yeah,
I-
sorry, go ahead. Yeah.
I do think no, like it's fine. I think that the big issue is that we still see the cosmic microwave background, right? Which is from when hydrogen combined, when neutrons and protons combine to form hydrogen. We can see that. We see that radiation. And so like that's pretty indisputable as far as we know. It's just getting from that point to the galaxies that we saw that is causing the confusion. So it's not throwing the whole Big Bang theory under the bus. It's just there's a big mystery there.
Well,
Okay.
talking
Sorry, go
about
on,
another speed bump, that brings me to the Hubble constant. One of the other things that I've been reading about in terms of James Webb, to follow up on what you were saying, Dave, is that observations have not settled an apparent discrepancy about the Hubble constant. Can you just take us through that in a way that hopefully won't break my brain?
This is so funny. This is just one of my favorite stories about astronomy ever. So the Hubble constant is the rate at which basically everything's expanding away from everything else. And for years, astronomers have like hardlined it's 50 or it's 100. Like you don't have to worry about the units, just the numbers I'm throwing out, 50 or 100. And there's this huge battle. Is it 50 or 100? And everyone has competing data to the extent that there is a license plate in Boulder, Colorado, where I went to college that says H0 is 50. And so people are hardlined about this. And over observations over the years, telescopes have gotten better and they've shrunk that down to about the 50s became 70s, the 100s became 75s, right? And I'm loose terms, big air quotes around everything I'm saying right now, but that's about where it was. And then we started observing gravitational waves. And gravitational waves are an independent way to calculate the Hubble constant. So everyone was like, hell yes, like we're going to prove it one way or another. Now that we see gravitational waves, this is the defining data set. And it came out like 72 plus or minus 3.
Thank you, LIGO.
What the difference? The bell curve runs right over both of them. Everyone was like, oh, damn it. Okay. Now, I haven't seen the latest numbers if JWST has even come out with a different data set, but this is just one of those great philosophies of science that people come in with biased opinions and they will find the data they want to find. And it cracks me up to no end.
So what happens if it's only ever possible to refine it that far? Is that a huge problem?
No, but people will feel like they've wasted their careers.
Their lives.
Problem for you.
For some people, it is going to be a massive problem.
Yeah. Now, for like
Oh.
introductory astronomy, 90% of society, it really doesn't make a difference. For some, like there is a trickle-on effect when you're talking about galactic and universe evolution, cosmology level concepts. Like you do use the Hubble constant in the mathematics. So yes, that can change models at that granular level. But in terms of our ability to wake up in the morning, it's fine.
Is there some
Right.
element of astrophysics that Star Trek does particularly right, or one that they do particularly wrong? Or just like maybe a small detail that they do right that you enjoy? Like I like the fact that they use the parallax effect when they do you look out the window and stuff like that. Like that's a nice touch. But
there's a lot. I think one of my favorite examples, and we just talked about, was the Heisenberg compensator. Like, I just think that's the most brilliant piece of science fiction writing, to just be like, look, we know we're breaking physics, but we compensate for it.
Right. At least they try.
One guy.
I think they're compensating for something.
Like, I acknowledge this and we move on from it. I mean, I think the warp drive is great, the way that it's talked about. There's a specific episode I particularly love in Voyager called Blink of an Eye, which is where the planet is evolving at a different speed relative to Voyager. And it's actually, because this is actually the only practical effect we have of Einstein's general relativity, which is the fact that GPS satellites do experience time different to how we experience time, fractions of nanoseconds, but it matters for GPS locations. Now in Voyager, in that episode, it was the opposite. The people on the planet were experiencing time faster than Voyager was. And that's due to the gravity well, but it's inverted. Like, that's not how it should be. That's not a normal gravity well. And they say that they have a tachyon core. And I'm like, heck yeah, because tachyon has an inverse gravitational presence. And so I was like, oh, hell yeah, that's so nerdy. But like, you explained that very well. And then you just don't, again, it's one of those things, don't scratch under the surface to say, well, how do they stay on the surface of the planet? Because then it all falls apart.
Right. Well, I think that's always the battle.
Don't forget your cord when you go outside, dear.
Well, we had like Steve Shives on a couple of weeks ago on one of our other podcasts, and he's I don't know if you know him, but he's like a YouTuber, always doing Star Trek stuff.
Yeah.
And he's always like, it doesn't matter, don't worry about the explanation. It's fake, guys. It's science fiction. But I'm always like, Steve, it's science fiction. Where you don't forget the science part. It's not just space opera. Try to, even if you create Heisenberg amplifiers or transporters or made up things that you can't really do in science, at least you're saying, well, we had this technological leap and then we could do this or that, right? So
and I always think, like, in my role especially, that like science fiction is a spectrum between science and fiction. I always equate it, because I'm also a big heavy metal fan. So it's like, when you meet other heavy metal fans, it's like, what kind of heavy metal are you into? And it's the same with science fiction, right? That there's a huge spectrum between them. And it's like, well, what kind of science fiction? Now, for the most part, we can agree, like, Star Trek kind of splits the difference. I think that that's one of the perfect examples of science to fiction. Some stories are hard science, some are hard fiction. Little energy beams with green hands that come and pluck the ship out. Fine. And so it really just depends on what kind of story you're trying to tell. And I think as a science advisor, we always have to trade, like, it's story and character and then the science. And if the story and character need to be told in a certain way that trumps the science, then like, let's just let it go. My favorite example of this was of navigating this was the musical episode of Strange New Worlds, because when they told me that they wanted to do this, I was like, go with the gods, have fun. and I look forward to reading it. And they were like, no. Like, we need a science explanation. Like, we need it to have, because it's so absurd. We have to Star Trek it. We have to have some science to it. And so, like, that was probably one of the hardest challenges I ever got, was trying to find just a couple of lines, right? But building this backbone of how this was occurring that could somehow be told in a somewhat sensical way that could explain it, that made it feel like Star Trek. And I think we got away with it. Like, I think it's really good. So yeah, it's tricky.
Subspace. There was something with subspace and music. And they were like, okay, sure. And then you're
multiverses colliding. There were bubbles, like improbability drive nonsense. Yeah.
Got to the Klingons. They're a boy band now. That's how
whenever we say it's not St. Vitus dance.
It was K-pop. It actually is Klingon pop. Yeah.
K-pop, Klingon K-pop. I love it. Yeah. Not like that Klingon acid punk.
Exactly.
True. I don't know if that is the same thing in Klingon as it is in actual K-pop. I mean, just me. I don't have your blood.
They have a different version of that. Yeah.
That's right.
Oh,
One thing I
awesome.
want to ask you
Oh,
before,
man.
we don't want to take your whole day away. We would, but we don't want to.
That's
Um,
right.
Yeah, you may have
Um,
other things to do
should-
with your hours.
there are different estimates and things like that, but to, try to compensate for what we see as the expansion of the universe, they say, the dark energy or dark matter could be 90% of or something like that, of the observable universe or something like that.
Yeah.
So that being the case, should dark energy and dark matter show up more in Star Trek?
So, that's a great question. So, I think dark matter and dark energy are two different things. Combined, they do make up about 95% of our universe. What we see, touch, feel, everything is 4% approximately. Everything else is this stuff called dark matter, which is something that we can see the gravitational effects of, that there's this huge gravitational presence in our galaxies and inner galaxy space, that we can't observe. We have no way of observing it. It doesn't interact electromagnetically, but it does interact gravitationally. So we see light bend around it, we see things spin faster than they should. So there's something there that we just don't have a way to see. Dark energy is even more not understood, which is simply the energy required to force the expansion of our universe. That it is not just the initial burst of the Big Bang that is causing the expansion. There is something continuing to push it apart. And it's a lot of energy. And because of energy mass equivalence, E equals mc squared, like we combine all of our universe into, like, yes, the combination, you think of it as mass or you think of it as energy combined. That's how we delineate all of it. So that said,
Hmm.
Star Trek, I feel, really does track a lot of scientific knowledge through the ages. Like you could almost go to the great discoveries and point to Star Trek when that was the big thing. For me, I love pointing out that, like, a lot of stuff in the next generation, especially in the technical manuals, were all run by superconductors, because that was the big thing in the 80s and 90s, right? It was like superconductor technology. And I think now we are starting to see more dark matter. Discovery had quite a few, explanations using dark matter. I used it to kind of think about where dilithium could come from, that our future discovery of dark matter that we make, because they talk about it in Star Trek, leads us to understanding where dilithium comes from, that there are these subatomic particles, some sort of subspace particles that have a gravitational presence that don't exist in our tangible universe that we can see it. So yeah, like I think dark matter, certainly because it's slightly more understood in that we can quantify it a little bit better than we can dark energy. We can see the effects of it much more tangibly than we can just the generalization of dark energy. Yeah, we start to see that more in Star Trek just because that's the science du jour, right, of the era. And so that starts to come in a little bit more. Same with genetics. I know you've talked to Professor Noor, and he's got a great, sort of tracking of genetics terms over the decades of Star Trek and how that tracks with our own understanding of genetics. So that's what I like. It's almost like a little litmus test for our current scientific knowledge, which is awesome.
Where can everybody find you? Or we've noticed on our banner here, you've got some books out there that people could certainly enjoy.
I do, yes. So if you like this nerdy science discussion, check out the Science of Sci-Fi as an Audible series. It's about, I think, 4 or 5 hours, and it's essentially going through the science of Newton gravity, Einstein gravity, and then how we see it all manipulated and played with in science fiction. So it's the Science of Sci-Fi. And then I also wrote a baby's board book called Star Trek, My First Book of Space. And so highly recommended.
Nice.
Lots of Star
Two
Trek
babies. I will purchase that one
You should.
immediately.
It's great and it's adorable. And then yeah, you popped up some Star Trek Adventures content. I just came out with a module
Yep.
for Dangers in Space. Yep. So if anyone plays Star Trek Adventures, the tabletop role playing game, there's some modules you can play in there that I wrote. And then other than that, I'm on Instagram and Twitch, Dr. Erin Mac, DrErinMac. And I have a YouTube channel, which has been quiet, but will be coming back. And regardless, you can go there to find links to all of the Science of Star Trek series that I did for the Star Trek franchise. We did a series on Star Trek Prodigy, and then I did some behind the scenes stuff for Strange New Worlds. So you can check all those out on YouTube. I'm everywhere.
Check it out on Star Trek Online.
The
I'm waiting for the
24th and
next
28th
installment.
century.
Yeah, and Star Trek Online, and watch Star Trek Prodigy, and just watch all the Star Treks. It's great.
Yep. Hashtag save Prodigy.
Yeah, exactly.
Okay, well, thanks again for joining us. This is a fascinating chat.
Indeed.
Thank you. This was fun. I love nerding out with some good astrophysics science questions rooted in Star Trek. It's perfect.
Yeah,
Perfect
thanks
way
so
to
much. It was
spend
a
a
real
morning.
pleasure.
This has been an honor,
Thank
an
you.
absolute
All
honor. Thank you so much, Erin.
Oh, thank you.
Yeah.
Yeah, it's been really fun. It's been a pleasure. Reach out anytime. Thank you, guys.
Awesome.
Thank you.
I guess there's only one thing left to say.
End transmission.